האם, לא יודע, 2020 זה נכון לקורס ככה. אוקיי, זה נתחיל משם. בוקר טוב. אבל רגע, אבל רציתי לשאול. לא, אהלן, מה קורה? אני לא באת לדיון. לדיון. זה בביטה. לא. בדיוק. יעקב בר. אבל שתיתי לפני 10 דקות אתה עושה, כאילו זה אחד לעצמך. אמרתי לך תגיד לו שידבר אנגלית. לא. מדבר אנגלית שנבין. לא, זה בעברית. לא, בעברית לא להבין בכוח. באנגלית אולי נבין באנגלית. יעקב, הגיע זמן יעקב. אתה יכול לסגר את הסמינר פה, 11. הנה רודי גם זה הגיע, הכל בסדר. כן, אין one minute. אתה רוצה לשבת פה אין בעיה? לא, הוא יפריע לי רק. Okay, today we have Guy Dagan as our speaker. Guy is a bachelor degree here at the department, and then he went to do his master's and the PhD in Weizmann, and now he's already 1.5 years in Oxford, and he's going to talk about clouds and things like this. Go ahead.
Thank you. Thank you all for having me. It's a great pleasure to be here. Today I'd like to talk about precipitation and what sets the amount of precipitation in our current climate system and in a future warmer climate. And the outline of today's talk, first of all I'll try to motivate why studying precipitation is important. And then I'll present you top-down constraints on the amount of precipitation using both water budget and the atmospheric energy budget. And then I'll move, at the last part of the talk, I'll move to talk about one specific driver for changes in precipitation, which are aerosols. So why should we care about precipitation? So we know that all natural fresh water on land arrive from precipitation, and this has huge implications for society, for life on Earth, for agriculture, and so on. And only from the atmospheric point of view, there is a two-way coupling between the general circulation in the atmosphere and the precipitation. So we would like to better understand precipitation from that aspect as well. Another reason to study precipitation has to do with the future. We expect that in the next few decades, the temperature on Earth will increase. And with it, we expect to see an increase in the amount of precipitation. But we don't know exactly by how much. So you see here a spread of different models that predict the increase in precipitation as a function of the increase in temperature. And different models predict different magnitude of increase, between 1 to 3% increase for each 1 Kelvin increase. So we're pretty sure that the increase would be, that there would be an increase, or the change would be positive. We are quite sure that it won't be as large as the increase in humidity in the atmosphere, which is predicted by the Clausius-Clapeyron relation. But we are not sure exactly by how much the global mean amount of precipitation is going to increase. And the situation becomes much worse when you look on local changes in precipitation. Local changes in precipitation are much harder to predict, and the uncertainty that involved in it is much larger. Local changes in precipitation could be on the order of a few tenths of percent rather than a few percent like the global mean, and they could be either positive or negative. And the general structure that people believe that it's going to be is that the wet regions, such as the deep tropics, are going to become even wetter, while the dry regions, such as the subtropics and the Mediterranean regions, are going to become even drier. And with the drying of the dry regions, we expect to see desertification or increase in the area of desert with time. So we see here the area over length of the dry regions of the desert as a function of time for a few scenarios of global warming, and in all of them we see some increase in the desert regions. This also has implications for our own region here. One thing to keep in mind that I'm not going to talk too much about, besides the mean amount of precipitation, if we are after the availability of water on land, we should also consider the amount of evaporation and the spread of the precipitation throughout the year. I think a nice visible example for it, you can see here two satellite images from Google Maps. This is the region I'm living here now, in Oxford, and this is where we are now. And both regions have the same amount of annual precipitation, roughly the same amount of annual precipitation, but completely different evaporation rates and spread of the precipitation. Here we have all precipitation in the 3 months. Over here we have it spread throughout the entire year, and much less sunlight available for evaporation. So this region is much greener than this region, even though they have the same amount of precipitation. Okay, so hopefully you're convinced that studying precipitation is important. So now let's look what we can do in order to better understand precipitation. And as I mentioned today, I'd like to present two top-down constraints on the amount of precipitation, using either the atmospheric water budget or the atmospheric energy budget. From the atmospheric water budget point of view, we know that the amount of precipitation, P, will be equal to the local source of water vapor, the evaporation, E. And because we are looking here on a given region in the atmosphere, closed region in the atmosphere, then we should also consider divergence or convergence of water vapor into this region. Okay? This is actually a mass budget, counting water molecules. From the atmospheric energy budget point of view, we can say that the amount of precipitation would be equal to the diabatic heating of the atmosphere, Q. And again, because we are looking on a given region in the atmosphere, we should consider divergence or convergence of energy, dry static energy, into this region. The diabatic heating of the atmosphere is actually composed of two different terms, a radiative term and a sensible heat flux term. Now let's try to better understand those terms. So if we're looking here on a given atmospheric region, atmospheric column. This is the surface, and this is the top of the atmosphere. So the sun illuminates this region with shortwave flux, shortwave radiation. Some of this shortwave radiation will be reflected back to space from the atmosphere or from the surface. So let's consider this arrow as the net shortwave radiation at the top of the atmosphere. In a similar way, we can look on the net shortwave flux at the surface. And the difference between the top of the atmosphere and the surface would go to absorption in the atmospheric column. Okay? We go to warm the atmospheric column. So we are looking here on the difference between the top of the atmosphere and the surface of the short wave flux. The same can be done for the long wave flux. So long wave is emitted from the surface. Again, let's look only on the net flux because there would be also a returning flux from the atmosphere to the surface. There also would be a net flux from the top of the atmosphere to outer space, and the difference between them would go to absorption in the atmosphere, or go to warm the atmospheric column. Okay, so the atmospheric radiative term is just the difference between the top of the atmosphere and the surface of both long wave and short wave fluxes. Another source of energy is the sensible heat flux from the surface. And because we are looking here on a given closed region in the atmosphere, as I mentioned, we should consider fluxes or convergence or divergence of energy into this region. And the last source of energy that we are after is the latent heat by precipitation. Okay? And if we look on it for long enough time scale in equilibrium, they all should be in balance. So we have here two top-down constraints on the amount of precipitation using either the water budget or the atmospheric energy budget. And those equations would be true if we look on a given region in the atmosphere, where we still have the divergent term in both of them. While if we increase the spatial scale that we are looking at some point, the divergent term will become inefficient anymore in compensating for imbalances in water or energy. And this would definitely be true on the global scale where we don't have divergence anymore. And then we have a pretty strict constraint on the amount of precipitation, which is exactly equal to the amount of evaporation and also to the diabatic heating of the atmosphere. Now, one word about the time scale of reaching to this equilibrium. Over here you see a simulation, a climate model simulation running for 10 years, and you see here the precipitation and the evaporation and their difference, and the precipitation and the diabatic heating and their difference. And you can see that the model starts away from equilibrium, and you see here monthly output. So after a month or two, it reaches roughly equilibrium, and the difference between precipitation and evaporation and between precipitation and diabatic heating is pretty small. Okay, so on a monthly time scale, roughly we reach already those equilibriums. Yeah.
What's not your times?
That's the question that I will try to answer.
Right?
Yeah.
We talk about future climate. You said that we're going to see the effect of, say, carbon dioxide in many years because it takes time for the system to adjust. And here you suggest that it's almost instantaneous, that the measure will stay immediately.
So the carbon dioxide affects the temperature, and this would affect the radiative budget. And so, or actually, the carbon dioxide affect directly the radiative budget would affect the temperature. And this would, with time, affect the radiative cooling. You'll have a change in the radiative cooling with time. But if you keep the radiative cooling roughly constant, then you'll reach to this equilibrium pretty fast. Okay, so we have here two different regimes. On a local scale where we still have the divergent terms, and on a global scale where we don't have the divergent term, and this system is much more constrained, much better constrained, because any perturbation to the precipitation will be balanced by changes in the evaporation and the diabatic heating. While on the local scale we have much more uncertainties because perturbation to the precipitation could be also balanced by the divergence or convergence of water or energy. And now I'd like to identify the breakdown scale between them. Okay, on what spatial scale can we start using those constraints? Should we go all the way up to the global scale to use them, or can we start using them on smaller scale? And I'll try to do that first for the water budget. So I'm taking here fields of precipitation and evaporation. This is from the analysis dataset, answer. And if I'm taking one minus the other, I'm getting, so if I'm taking P minus E, I'm getting the minus the divergence of water vapor, or the convergence of water vapor. And you see here the fields of P minus E for the analysis data set that involve also observation fields, and one of the climate model that is used to predict climate change and as a part of the Simul 5 simulations. And we are getting those fields that you see here. We get net precipitation or net convergence of water in the deep tropics, net divergence or net evaporation at the subtropics and especially at the east boundaries of the ocean, and net precipitation at mid and high latitude. And now I'd like to take those fields and start averaging them over a larger and larger scale. Okay, so for each point, I'm drawing a circle with a given radius around it and average over this circle, and I'm going and increasing the radius continuously over here. Okay? And you can see that once I'm averaging over a few thousand kilometers, the pattern that we see here almost completely vanishes away. And now I would like to ask, on what spatial scale should I average over to close the water budget locally to a given region? Okay? Meaning that P will be equal to E to within, let's say, 10% in this case. And then I'm getting those fields over here. This is the scale that I need to average over to close the water budget for each point over the globe. And you see that we get a certain pattern. First of all, we see those blobs at the east boundaries of the ocean. Those are created because if I'll start the averaging just at the center of a confined region of net evaporation, I'll need to average over a larger scale to close the water budget. While if I'll start the averaging just at the transition between net evaporation and net precipitation, it would be easier to close the water budget. I won't have to average over so large scale. Another thing we can see from here is that at high latitudes, the averaging scale is large. It's harder to close the water budget locally. And this is because of advection of water vapor with the atmospheric circulation from low to high latitude. Okay, so the atmospheric circulation brings with it water vapor from low to high latitude, and hence it's harder to close the water budget locally at high latitude. And I can do the same type of calculation for many models. In this case, we did it for 39 different Simul 5 models that are used to predict climate change for two reanalysis data sets of MCT and WF, and some additional simulation of our own that I'll show in a minute. And this is the result that we get. What we see here is the average scale that one needs to average over to close the water budget to a given level. Okay, so for example, if we require the water budget to be close to within 10%, we have to average over roughly 4,000 kilometers. And if we leave for a minute aside this curve, you can see that all the rest of the data sets and all the rest of the models gives roughly the same trend and the same value. The trend itself that just means that if you require the water budget to be close to a stricter level, you have to average over a larger scale. This makes sense. Another thing we can see from here, and this might answer your question, is that we do not expect to see a large shift in this scale with global warming, because we ran this calculation for both future predicted climate with all the models, what we call the RCP 8.5 scenario, a relatively pessimistic scenario of fast increase in greenhouse gases, and the historical climate, and they give roughly the same value. Now, going back to this unique curve, I already mentioned that it looks like the structure, the existence of land and ocean determine to some degree this scale, because it creates those blobs, those confined regions of net evaporation on the east boundaries of the ocean, for example. So in order to study the effect of land on this scale, we ran a GCM named ICON with and without land. Okay, in aquaplanet configuration, in a planet without land and in a planet with land. The one with land, this one, the purple one, gives the same values as the rest of the data set, while the one without land, the aquaplanet one, shows higher sensitivity. In an aquaplanet configuration, world without land, instead of having those confined blobs, we will be in a zonally symmetric world, in which we'll have bands of net precipitation and net evaporation, one next to the other. And in a zonally symmetric world, it would be harder to close the water budget to a strict level. Okay, one would have to average over a larger scale. So in a way, the existence of land determined to some degree the scale because it creates those confined blocks. Okay, so we did it for the water budget, and we saw that one need to average over roughly 4,000 kilometers to close locally the water budget. Now let's do the same for the energy budget. Over here you can see the multi-model mean P minus E. Okay, so the convergence of water vapor, and this is the P minus Q, or the divergence of dry static energy. Over here we see them in the native resolution, and you can see that at least in the tropics, they are highly correlative. And indeed, if we look on the zonal mean picture, so we see here this is south, this is north, and we see here the zonal mean. In blue, we see the convergence of water vapor of all the different models, and in red, we see the divergence of dry static energy for all the different models. And you can see that in the tropics, they are highly correlative. In the deep tropics, we have convergence of water that produced a lot of precipitation in the ITCZ, and this precipitation release latent heat that then have to diverge away. So at places that we have convergence of energy, we have divergence, the places that we have convergence of water, we have divergence of energy. At the subtropics, it's the other way around. We have convergence of energy and divergence of water. And the correlation between them breaks at the mid-latitudes. And above it, at high latitudes, we have convergence of both water and energy. And this is because of the circulation in the atmosphere that brings water and energy from low to high latitude. So we have convergence of water and energy at high latitudes. Okay, going back to this figure that we saw before, we are taking those fields in their native resolution and again averaging them over larger scale. And at least from here, it looks like the pattern vanishes faster on smaller scale for the water budget than for the energy budget. And indeed, this is the case on average. Over here, we see the average scale of closure of the energy budget over the entire globe, the energy budget only in the tropics, the water budget over the entire globe, and the water budget only in the tropics. Okay, so two things we can see from here. First of all, we see that the scale of closure of the energy budget is larger than the scale of closure of the water budget. Okay? And this would suggest that the water budget is a better predictor, a predictor that will become more efficient or efficient on a smaller scale than the energy budget in predicting changes in precipitation. Another thing we can see from here is that the scale of closure only in the tropics is smaller than the scale of closure over the entire globe. And this is true for both the energy budget and the water budget. And this is because of this advection of water and energy from low to high latitudes with atmospheric circulation. And this would suggest that using those constraints would be more efficient at low latitudes compared to high latitudes.
Is it not because of the curvature of the globe? Near the poles, actually you have this.
No, so what we are doing here, we are looking on the relative. So it's all normalized to the amount of precipitation. So we are looking on the difference relative to the local amount of precipitation. And in the high latitudes, large fraction of the precipitation is due to advection of water from low latitudes to this region. While it's true that the low latitudes lose the same amount of water as the high latitudes gain, but compared to the local amount of precipitation, this is a small fraction.
Isn't it because you have such huge precipitation in the tropics, so you normalize the precipitation, so this is why you get smaller scale of the tropics?
it's because you get a lot of precipitation in the tropics, and most of it is coming from evaporation, local evaporation in the tropics. While in the high latitudes, most of the precipitation is coming from water that was evaporated at low latitudes and injected to high latitudes. Okay, so we did it. So until now, we looked about what sets the amount of precipitation in our current climate. Now I'd like to shift perspective to future changes in precipitation. So instead of looking on P, let's look on delta P. And delta here represents, for example, future climate minus previous climate. And changes in precipitation would be equal to changes in evaporation minus changes in the divergent term. And changes in the divergent term could be caused by two main reasons. They could be caused by changes in the large-scale circulation of the atmosphere that cause changes in convergence or divergence of water with air. This is known as the dynamical contribution, and this is the hardest part to predict. But it could also be caused by changes in the thermodynamics of the atmosphere, or the amount of water vapor in the atmosphere, that even for a given air convergence or divergence, they would cause changes in the water vapor convergence or divergence. And the second part is easier to predict because at least we think it would follow the Clausius-Clapeyron relation. So we know more or less to predict this part. And for the same reasons as I presented before, for large enough spatial scales, the contribution from changes in the divergent term would become small, and so changes in precipitation would be exactly equal to changes in evaporation, which are known to be relatively small and well constrained by the system energy budget. Okay, you don't have enough energy to evaporate more water. Now, on smaller scale than that, the contribution from the divergent and changes in the divergent term will still be important, and so changes in precipitation won't be very well constrained, and they could be much larger or smaller than the global mean. Okay? And now I'd like to identify this, identify the breakdown scale between those two regimes. So in order to represent changes in precipitation here, I'm taking a future prediction of the climate that was done by the IPCC. The simulation that was done by the IPCC, many models were run until the end of the century with few scenarios of climate change, or few scenarios of rate of increase in greenhouse gases. And in this case, I'm taking the most pessimistic scenario, the RCP 8.5, a relatively fast increase in temperature. Okay? And I'm taking the difference between this scenario and the historical climate for each model. And for each model, I'm getting fields of changes in precipitation like that. And we can again average them over larger and larger scales. And we can do the same for the changes in evaporation. And then we can look on the correlation. This is the correlation between changes in precipitation and changes in evaporation as a function of the averaging scale. Okay, so, and you can see that for small averaging scale, the correlation is pretty low, meaning the changes in precipitation are not caused by local changes in evaporation, but rather by changes in the dynamics of the atmosphere. And the correlation increases with the special scale of averaging, and it crosses the 0.5 level at roughly 4,000 kilometers. Okay? So what we are trying to say here is that at scale smaller than that, changes in precipitation would not be determined by local changes in evaporation, but the dynamical contribution would dominate. And so changes in precipitation could be much larger than the global mean, or even have the opposite sign, meaning be negative.
What? 10,000 kilometers, it's pretty low. It's out.
Yeah, it's only in the tropics. It's only between minus 40 to 40. So on the global scale, if you go all the way up to the global scale, it's much each one. Whatever go, yeah.
10,000 kilometers in tropics is pretty big.
Yeah, it's 0.8. I would say it's pretty high. Yeah, so on small scale, the dynamical contribution still dominates, but on scale larger than that, the change in precipitation will start to approach the global mean change. And a few years ago, Muller and Gorman did the same type of calculation for the energy budget. So we see here the correlation between changes in precipitation and changes in the diabatic heating of the atmosphere as a function of averaging scale. And you see still, you again see this increase in correlation, but in this case, it crosses the 0.5 level at larger scales, at 6,500 kilometers. And I think that this is consistent with the fact that I showed you that in our current climate, one needs to average over a larger scale to close the energy budget than to close the water budget. Okay? And this again suggests that the water budget is a better predictor for changes in precipitation than the energy budget. Any questions? So yeah, until now I presented top-down constraints on the amount of precipitation, and I showed you that the water budget is a better predictor on smaller scale, become an efficient predictor on smaller scale than the energy budget. This would be true for any driver of changes in precipitation, either natural or anthropogenic. Okay, it doesn't really matter. Now I would like to focus on one specific driver for changes in precipitation, but maybe the hardest one to predict, which are due to anthropogenic aerosols. Aerosol could affect the amount of precipitation either by interacting with the clouds, and for those who've been here last week in my seminar, I presented a lot of work about that. But aerosol could also interact with the amount of, or affect the amount of precipitation by interacting directly with the radiation. And today I'd like to focus more on that. So for those who don't know, aerosols are tiny particles, solid or liquid particles that are suspended in the atmosphere, and they could be released due to anthropogenic activity such as burning of fossil fuels, and also interact with the radiation by either scattering the incoming solar radiation, and this would usually be caused by lighter colors aerosols such as sulfate aerosols. But they all could, and this would, scattering of the incoming solar radiation would mean that some of the incoming solar radiation would be reflected to space, and less radiation would reach the surface. So the lower atmosphere would become colder with time. The aerosol could also interact with radiation by absorbing some of the incoming solar radiation. This would usually caused by darker colored aerosols, such as black carbon or soot. And this would cause warming of the atmospheric layer in which the aerosols are found. But again, it would also cause less radiation to reach the surface. And in order to study those effects on precipitation, we use the global circulation model named ICON. And in this case, we use it in a simple form without land in an aquaplanet configuration. And we put a plume of aerosol, a Gaussian distribution in space of aerosols, and we can change the size of the plume. In this case, we use 4 different radii of plumes, so 4 different sizes of plume, 2 different radiative properties of aerosols, so either relatively scattering aerosols with single scattering albedo of 0.95, so like the sulfate aerosol, for example, or more absorbing aerosols, such as black carbon, and we put the plumes of aerosols either in the tropics at the equator or in the extratropics at 40 north. And in this case, we are directly perturbing the atmospheric radiative term because of the interaction with the aerosols, and we examine whether it affects the amount of precipitation. Yes, and over here you see the atmospheric radiative term of all the different simulations. And on the global mean response, so you see here the global mean radiative term and the global mean precipitating term. Over here you see the reference simulation with no anthropogenic aerosol, this is the star here. And all the different simulations with the anthropogenic plume of aerosols all roughly lies on the same line. This trend just means that the larger perturbation to the radiative term that we impose, the larger the response, or the larger the reduction in precipitation. And for the global mean response, you can see that it doesn't really matter where the plume is located, either at the tropics or the exotropics, they all follow the same trend, the same line. However, for the local response, it does matter where you put the plumes of aerosols. We see here two different simulations with the same plume characteristics, same plume size and same plume radiative properties, but one time it's located in the tropics and one time it's located in the exotropics. And you can see that it generates roughly the same perturbation to the radiative term. There are differences that I'll talk about in a minute. But it generates completely different perturbation to the precipitation term. In the tropics, we get a local increase in the amount of precipitation, very strong local increase in the amount of precipitation, even though the global mean response was negative. While in the exotropics, we get a local reduction in the amount of precipitation. And this contrasting response cannot be explained by the relatively small changes in the sensible heat flux. So just looking on all the different simulations, so over here we see in blue, these are the tropical simulation, different sizes of plume, and in red we see the extratropical simulation, again different sizes of plumes, and we see here the radiative term, precipitation, sensible heat flux, and the divergent term. This is the more scattering aerosols, and this is more absorbing aerosols. First of all, you can see that we always get a positive, we impose the positive perturbation to the radiative term, but we get roughly 15% larger perturbation in the tropics compared to the exotropics. And this is even though we normalize for the different radiation in the tropics and in the exotropics. And I will talk about, this is caused by cloud feedbacks in the perturbation, and I'll talk about it. But always positive perturbation to the radiative term in the tropics cause positive perturbation to the precipitation, and a negative perturbation to the precipitation in the exotropics. And why is that? In order to understand what is going on here, let's look on cross sections through the center of the plume. In this case, we are looking on zonal cross sections, so west-east cross section through the center of the plume. And we see here the response of the temperature and the three components of the wind speed. So we see here U, which is westward wind, V, which is northward wind, and omega, which is vertical wind. And this is for the tropical simulation, and this is for the extratropical simulation. Focusing first on the temperature response, in the tropics we see that we get a more uniform warming of the troposphere, and even a stronger warming of the upper troposphere, even though the aerosol lies of the lower atmosphere. While in the exotropics, we get a more localized, more confined warming at the lower atmosphere. Looking on the dynamical response, in the tropics, we see that we get a positive response in one direction of the plume and a negative response in the other direction. So we get convergence at the surface, which is coming with a very strong increase in vertical velocity. And increasing the vertical velocity in the atmosphere generates deep clouds that generate precipitation. And this is why we get the local increase in precipitation in the tropics. While in the exotropics, we don't see the same response in terms of the dynamics, but we do get a wavy pattern that is generated by the local heat. Now, looking on the regional cross-section, so in this case we see south-north cross-section through the center of the plume. We again see this more uniform warming of the tropical troposphere in the tropics and a more localized heating in the exotropics. In the tropics, we see this increase in vertical velocities that generate deep clouds and a lot of precipitation, and this is coming with an increase in the tropical, in the heavy circulation over here, next to the center of the plume, which we don't get in the exotropics. So what is going on here? In the tropics, we have a local heating that generates like a monsoon circulation. Okay? We have a conversion of the surface, upward motion of air that generates deep convective clouds that produce a lot of precipitation. And this large-scale circulation diverges the energy to large distances. While in the exotropics, because of the effect of the rotation of Earth and the Coriolis force, we cannot generate this large-scale circulation because air that would start to diverge into the center of the plume would deviate away by the Coriolis force, and we won't get this large-scale circulation, so we get a much more localized heating, which have which means that you have to get a reduction in the amount of precipitation in order to maintain the energy budget. Now, I showed you that we got roughly 15% increase in the radiative term in the tropics compared to the exotropics. And why is that? Even though we impose the same perturbation, this is because of the cloud radiative effect. So in the tropics, we get deep convective clouds that interact with the radiation as well. And the cloud interact with radiation, clouds have a contrasting effect, a contrasting interaction with radiation. Clouds are white, they're usually whiter than the surface, and so they reflect more of the incoming solar radiation with what will happen without the clouds. So they have a negative shortwave effect. But clouds are also colder than the surface usually, and so they have a positive long wave effect. They emit less long wave radiation to space than what would happen if you won't have clouds. And the net cloud radiative effect is the sum of those two contrasting responses, and is a function of the cloud type, or actually the cloud optical depth and the cloud top height, or how cold is the cloud top. In our case, since we create a lot of deep clouds with high top, we have a positive radiative effect. Okay, we have the long wave effect wins, and so we have in the tropics an increase in the radiative perturbation that we impose on top of the positive feedback that increased the radiative perturbation that we impose. So
But you show that the net effect is negative, which means cooling rather than that it goes in opposition to the warming perturbation.
no, it's positive. We impose the same amount of perturbation, radiative perturbation in the tropics and in the exotropics. But in the tropics we get deep clouds and deep angles that create larger radiative perturbation, positive radiative perturbation because of the long wave effect.
You have net warming. That's interesting.
Net warming, yeah. So what is happening here? We've imposed the same amount of perturbation in the tropics and in the exotropics. The cloud feedbacks to the perturbation increase the perturbation in the tropics. It doesn't really affect it in the exotropics. The increase in the precipitation produced a lot more energy in the tropics, and it doesn't really counteract by the small changes in the sensible heat flux. So a lot of energy have to divert away. Divert away by this large-scale circulation that is formed in the tropics. While in the exotropics, we cannot form this large-scale direct circulation that will divert away the energy. So the positive perturbation that we impose must be counteracted, at least to some degree, by reduction in the sensible heat, in the precipitation, in the sensible heat flux, and only small amount of energy can divert away. Now, you may ask yourself, where is the border between the tropics and the exotropics? So I showed you a positive response in the tropics and a negative response in the exotropics. And in order to understand where is the border between them, we conducted continuously increasing the location of the plume. Simulation with, so this is just at the equator, at 10 north, 20 north, 30 north, and so on. You consider that all the perturbations are positive, but they have different magnitude because of the cloud feedbacks to the perturbation. And this is the response of the precipitation, which is positive at low latitudes and negative, or entirely negative from 30 onward. But even if you look on the 21, actually the plume is located just at the blue region north of the positive one. So over here we see the response of temperature at the center of the plume, and at 20 north it's already negative at the center of the plume because the plume is located just over here. And the positive is already at the tail of the distribution of the ocean. So actually the transition between an increase in precipitation at the tropics and a decrease at higher latitudes occur at pretty low latitudes. Okay? It's not a pure difference between tropics and exotropics, it's the difference between the deep tropics and all the rest. And why do we get this transition at such low latitudes? Just to show you again, we see here cross sections through plume, and we see here the response of the temperature in the simulation in which the plume is located at the equator, at 10 north and at 20 north. And you can see that actually the transition between increase and decrease occur at roughly 10 north. And why is that? Over here you see a map of the distribution of tropical cyclones in the last few decades. And you can see that tropical cyclones don't form or don't exist just at the equator. In order to form a tropical cyclone, you have to be, I don't know, 7, 8 degrees away from the equator. You have to have a certain amount of Coriolis force in order to generate the circulation. And the same amount of Coriolis force that is enough to generate a tropical cyclone is already enough to prevent this direct thermal circulation that we saw at the equator in our simulation. Okay? So the same amount of Coriolis force that is enough to generate a tropical cyclone would be enough to suppress the increasing precipitation that we saw in the deep tropics and cause a decrease, local decrease in precipitation. Okay, so until now it was all based on simulations that were done in aquaplanet configuration. Now shortly I would like to show you what is the effect of land in those simulations. So we conducted a simulation with plumes of aerosols on GCM with land in this time, and we put the plumes of aerosol either at the tropics or at the extratropics, either over land or over the ocean. And to make a long story short, and in this case we use either absorbing aerosol with single scattering albedo of 0.8, like in the last time, or completely scattering aerosol. So single scattering albedo 1, not like the last time. Completely scattering, no absorption at all, and with completely scattering aerosols, you don't have any perturbation to the radiative term of the atmosphere, but we still get perturbation to the precipitation term. And why is that? This is because of the, if we have completely scattering aerosols, for example here over North America or over Asia, then less radiation reaches to the surface, even though we didn't perturb the atmospheric radiative term. Less radiation will reach to the surface, so we have surface cooling, where we have a plume of aerosol. This also caused an increase in the pressure, the air pressure, at the center of the plume. So we get like what we call a blocking event, a high system pressure that stands at the same location for long enough time. And this caused an anticyclonic circulation around the plume center, and hence subsidence, decreasing vertical velocities at the center of the plume, which prevent the cloud development and cause reduction in precipitation, even though we didn't affect the atmospheric radiative term. And this is caused by the cooling of the lower atmosphere. So over land, the main difference between land and ocean is that over land, the sensible heat flux is more effective than over the ocean. To sum up, so I presented two top-down constraints on the amount of precipitation using either the water budget or the energy budget, and I showed you that, at least on average, the water budget is a more efficient constraint on the changes in the amount of precipitation due to any forcing. And at the second part of the talk, I talked about more bottom-up or process-level studies of aerosol effect on precipitation due to interaction only with radiation. And I showed you that aerosol could affect the amount of precipitation by interacting with radiation, and they can do it differently at different latitudes, depending on the response of the general circulation of the atmosphere. And that the cloud feedbacks to the imposed perturbation could affect also the magnitude of the perturbation of the radiative. By that, I'll finish and I'll be happy to take questions.
So the alpha simulations with tropical aerosol. So there's a diffusion situation locally and globally. So is that?
No, the topic there is a lot. Oh yeah.
So in terms of so it's not just a actually pronounce that. So it's because the aerosols are there's less cohesion surface. I was just trying to understand how exactly where exactly the goal is used. So it's not.
So we have absorption in the atmosphere. So we must get a decrease.
Okay.
You can look at that as if we added greenhouse gases. We fixed the surface temperature, but we added the greenhouse gases, so we decreased the radiative cooling of the atmosphere. It's the same type of perturbation.
I ask for a point of view of a geologist. So you talk about several feedback mechanisms. But let's say, what about feedback mechanisms that are related, for example, I give you an example, expansion of the desert bed.
Yeah.
So we know that there is sometimes, when we look on the paleoclimate, that the desert has expanded and the desert contracted. So how this kind of consideration is going into these models?
Yeah. So I think, I have it here. So I don't know if it's hard to see, but so this one is previous climate, and this is the future predicted climate, and we expect to see desertification or increasing the happy circulation wave, meaning that the subsidence rhythm would propagate to the pole in both hemispheres. And it's not significant in terms of compared to the variability, the intermodal variability, but we do see some increase between the future predicted climate and the previous climate. And I think that this is because of the expansion of the happy circulation. So what's determined this scale in a way, in the tropics at least, is the difference between the subtropics and the tropics, where we have net evaporation in the subtropics and net precipitation in the deep tropics. And if you increase the distance between the subtropics and the deep tropics, like by expanding the happy circulation, you'll increase the scale. But at least for the next century or the next century or so, it's expected to be 100 kilometers or 200 kilometers, and it will be small compared to those.
Your aerosol perturbations remind me the hypothetical aerosol perturbation, like the real aerosol perturbation in Southeast Asia, and which is called the elevated heat pump hypothesis that is enhancing the Indian monsoon. Did you make the linkage between the two?
We are working on it now, yeah. We are working on connecting it to the monsoon effect, the aerosol affected monsoon circulation in East Asia, and also to the biomass burning in Africa, which is occurring just at the equator. And I think we can see the same type of response that we saw here at the tropical simulation over there.
I wanted to ask you, what is the sensitivity, what do you think the sensitivity of using another RSP scenario? Because you took the
we use 39 different models, and the variability between the models is pretty small, and two different scenarios here, and they show roughly the same value. So I don't think that using the different scenario will fall somewhere between this point and this point. So compared to the variability, the intermodal variability won't be significant. Because any other scenario is somewhere between them. This is the most extreme one.
Yeah. So this is a general question which I'm going to help me understand something. So if you think of healthy sodium, right, 2 to 3% of increase in precipitation per degree, and you compare that to Klass's Clapper on the 7% per degree of water in the atmosphere, that means an increasing residence time of water in the atmosphere, right, on the order of 5% per degree. So if you think the RCP 8.5, say, increase of 2% of 2 degrees, that would give you an increase in residence time of about 10%. Now, if increase in residence time is a function, is a spatial function as well, right? If you increase in residence time, your effect of water, of an air parcel gets bigger, then you would expect, just based on the temperature, that the radius will get larger, which is what you're seeing.
Yeah.
So maybe, and then that also answers the question how you go from one RCP to another, which is based on the temperature difference.
Yeah.
Or the difference between Klass's Clapper and Healthy sodium. If you convert that, that will give you a spatial extent.
So we do get some spatial extent, but it's small compared to So yeah, if you talk about spatial structure, it's like, I don't know, 100 kilometers compared to 4,000. So this is the roughly the magnitude of the expansion. So it's not large compared to the intermodal variability in the 75. But I do think it's there. I mean, even though you can't say it's statistically significant, I think it's physical. I mean, I do expect to see.
Okay, Guy, thank you very much.
הוא גם יודע הכל, אני לא יודע, כשאתה אומר היסטוריקה, לא, כל הדבר כאן הוא לא,
אני מזכיר ש...
אלון? אתה מבין, השאלה אם זה היה קופץ על זה פתאום, אם זה עדיין היה... עדיין לא עכשיו?
לא, זה שיעור השלמה. זה חד פעמי. זה הזמן היחיד שהיה נוח לילד, אבל בינתיים אני לא רואה אותו.
יש כל מיני נושאים, אבל אני לא יש להם אחרים. הבעיה היא שצריך לשמוע. כן, אני קצת זהו, אני שוב אני אשאר. מה בו ג'אמבו? בעיקר יש לנו סוגרת. יש לך כל הזמן. נכון, אני חושבת ש... אני כל עכשיו כל ינואר. זה לא תהליך קולוניארי, זה לא אפשר לבזבז זמן. כן, כל אחד ממציא, כל הכבוד, אבל
אנחנו משלמים. לא משלמים רגע. אני עכשיו...
זה סיפרת.
ושהעניין יידון, שהוא בן בשביל, והעניין יידון, בסוף כמו לא מספיק, שיש אפשר להתחממה בין... הילדים באמת צריכים לדעת את זה. אז אני אומרת, חבל שומע לכם, לא עניין אתכם, אתם תקבלו הודעה אם נוסעים או לא נוסעים, וכל מה שקורה בבניין הבינון, זה לא קשור לכם, ובאמת לא צריכים להיות מאוד וחבל לי מאוד שומע לכם. אני פועלת לו זה שהסכים את השטן, הוא כרגע מתנדב, שופט תחליט אם עשו או לא עשו, ועשיתי את זה מאוד פשוט. אז אתה אומרת, כן, נכון, באמת אנחנו באמת עושה, מה אתה
אבל אין דרך על זה, אבל באופן כללי.
לא כמו בפסולי, חבר'ה. מי יודע מה היה במסלול? אני אמרה לך לתת שיעור השלמה,
אין מילה שלי.
אז אני יכולה אחר כך להחליט שסיימתי אזורי הפרטה, כי זה היה מאוד בשעה הזאת. ראית את האימון שלי?
ראיתי.
הם השתמשו ברודיום כיסוד קיול, ואז הם פתאום מוצאים 20 ppm זבון מאיתנו. זאת אומרת, בטח בא עם אחד מהבקבוקים, צריך לראות מה... אז אנחנו מחפשים יסוד אחר, אנחנו רוצים לדעת מה רמות הזיהום שקיימו.
איפה זה נמצא?
יש שם קלסל מעל ה... יש שם MSDS,
נכון.
תעבור על כל ה...
זה יכול להיות מהגיליום? בדרך כלל אנחנו מוסיפים בהגיליום אחרי שהם מוסיפים את האנליזה.
נכון. אז תסתכל אולי אם יש סיום. אז אולי תסתכל אולי בבקבוק של האירידיום גם, במוצק יכול להיות. תסתכל, בסדר, תעשה ככה איזה שם, תעבור שבוע, בסדר. זה שהשיעור התחיל, למי הוא התחיל? אתה בוא ללמד פה?
הייתי אמורה, אבל...
אבל ביקשתי אתמול